Hello, future teacher! Welcome to our comprehensive guide to passing the elementary education grades 1 to 6 test, proudly presented by teacherpreps.com. This exam assesses your readiness to teach elementary school with 150 multiple-choice questions in 4 hours. Here's what you can expect to receive on test day. Science and social science is 13% each, with 15 scorable items per section, integrating crucial facts and theories. Wondering how to prepare for all these subjects? TeacherPreps.com provides targeted study guides, video lessons, and practice tests to boost your readiness for test day. Sign up at TeacherPreps.com now and make passing your elementary education test simple. Hey, future teacher! In this lesson, you will learn the key concepts about science instruction that will help you ace your teacher certification exam. Are you ready to begin? If so, let's get started. Integrating reading strategies in science. First, let's talk about reading strategies. Science texts can be dense, packed with new vocabulary and complex ideas. Here's how you can help your students navigate these texts. Vocabulary development. Introduce scientific terms within context. Use visuals, create word walls, or have students participate in making their own glossaries. This helps demystify jargon, making content more approachable. Reading comprehension. Employ strategies like summarizing, questioning, and predicting to deepen understanding. Encourage students to annotate texts, highlight key information, and discuss their thoughts. This active engagement helps transform passive reading into a more dynamic learning experience. Informational texts. Utilize texts that provide real-world applications of science concepts. Teach students how to extract and interpret scientific data, enhancing their ability to apply what they learn in practical contexts. Applying mathematical practices in science. Mathematics is the backbone of scientific inquiry, providing the tools to quantify and solve problems. Here's how to integrate math into your science teaching. Quantitative analysis. Engage students in activities that require measuring, calculating, and using statistical methods. Whether it's analyzing environmental data or calculating chemical reactions, these skills are essential. Problem solving. Foster mathematical problem-solving skills within science contexts. Set up scenarios that require students to apply their math skills to figure out solutions, reinforcing the link between the two subjects. Data representation. Teach students how to create and interpret various forms of data representation, such as graphs, tables, and charts. This is crucial for communicating scientific findings effectively. Utilizing science content materials. To bring science concepts to life, use a variety of materials, hands-on materials. Incorporate tangible materials that allow students to explore and experiment. From simple lab equipment to interactive models, these resources make abstract concepts concrete. Digital resources. Leverage technology like simulations and interactive websites to complement traditional materials, offering students a multimedia learning experience. Real-world applications. Connect science lessons to real-life scenarios. This not only shows the relevance of science, but also sparks curiosity and motivation among students. Enriching science. Instruction. To truly enrich science instruction, consider the following. Differentiated instruction. Tailor your teaching to accommodate various reading levels and mathematical abilities. This ensures that all students, regardless of their starting point, can access and engage with the content. Content connections. Explicitly link science concepts with the necessary reading and math skills. This helps students see the interconnectedness of their learning and understand why all components are essential. Culturally responsive materials. Choose materials that reflect the diverse backgrounds of your students. This inclusivity not only enriches learning, but also helps students see themselves as scientists. Strategies for all learners. Finally, ensure your teaching strategies accommodate all learners. Scaffolding. Provide step-by-step support for students as they tackle complex texts or problems. Gradually reduce support as their competence increases. Multimodal learning. Offer content in various formats, visual, auditory, kinesthetic, to cater to different learning styles. Assessment and feedback. Use diverse assessment methods to gauge understanding and provide constructive feedback, guiding students in their learning journey. Ready to see how well you've grasped these concepts? Head over to teacherpreps.com and take our science instruction practice test. Thanks for watching, and I'll see you in the next lesson. Hello, future teacher. In this lesson, you will learn all about the history and nature of science in order to help you get totally prepared for your teacher certification exam. If you're ready, let's begin by learning about the ancients and the foundations of science. Our story begins with the ancient civilizations, the true pioneers of scientific exploration. The Egyptians and Babylonians advanced mathematics and astronomy, setting the stage for future discoveries. Meanwhile, the Greeks were busy developing natural philosophy. Thinkers like Aristotle and Plato pondered the cosmos and natural laws, laying the groundwork for modern science. Understanding these foundations helps us appreciate the continuous thread of inquiry that science weaves through history. Contributions from the Middle Ages. Fast forward to the Middle Ages, where Islamic scholars became the custodians of ancient knowledge. They translated Greek texts into Arabic, enriching fields like optics, medicine, and astronomy. In Europe, the intertwining of science and religion shaped the scientific landscape, with the Church playing a pivotal role in guiding scientific inquiry. The tides of change. The scientific revolution. The 17th century brought about the scientific revolution, a period of profound change and discovery. This era challenged the geocentric view of the universe with Copernicus's heliocentric model. Figures like Galileo supported this with telescopic observations, while Kepler and Newton revolutionized our understanding of planetary motion and gravity. This period was not just about new theories, but marked a shift towards empirical evidence and systematic experimentation, forming the bedrock of the scientific method. Empirical evidence and the scientific method. The scientific revolution heralded a new approach to inquiry, emphasizing observation, hypothesis, experimentation, and conclusion. Philosophers like René Descartes and Francis Bacon championed rationalism and empiricism, advocating for knowledge based on observational evidence. This methodological shift was crucial as it promoted a more rigorous, evidence-based approach to science. The legacy and influence on society. The impacts of the scientific revolution transcended academia, influencing the Enlightenment and shaping modern philosophical thought. It underscored the power of the scientific method and the importance of challenging established beliefs with evidence, principles that remain central to scientific inquiry today. The role of observation in science. Observation is the cornerstone of scientific inquiry. It involves meticulous noting and recording of natural phenomena, leading to questions and hypotheses. Through observation, scientists detect patterns and anomalies that challenge existing knowledge and spur further investigation. The centrality of evidence. Evidence is the backbone of science, providing empirical support for theories and hypotheses. The credibility of scientific knowledge hinges on the quality and quantity of this evidence, gathered through various methods like experiments and simulations. Major scientific discoveries and their impact. From the microscopic to the cosmic, scientific discoveries have reshaped our world. Antony van Leeuwenhoek unveiled the microscopic universe, while Newton's laws framed classical mechanics. Einstein's relativity redefined our understanding of space and time, and Darwin's theory of evolution explained the diversity of life. Each discovery not only advanced knowledge, but also had profound societal impacts, driving technological and medical advancements. The scientific method in action. The scientific method is a dynamic process involving observation, questioning, hypothesizing, experimenting, and concluding. This method is crucial for minimizing bias and ensuring the reliability of scientific findings, embodying the rigorous nature of scientific inquiry. Science as a dynamic and collaborative endeavor. Science is continually evolving, driven by new evidence and collaborative efforts across disciplines and borders. This dynamic nature ensures that scientific knowledge is robust, diverse, and reflective of the global community. Scientific ethics. Scientific ethics are the backbone of research integrity. Key principles include honesty, objectivity, integrity, and respect for intellectual property. It's essential to conduct all scientific work with carefulness and openness, ensuring confidentiality and responsible publication. We'll discuss how these principles guide researchers in maintaining high ethical standards and the consequences of ethical breaches, such as career impacts and the erosion of trust in science. Logical reasoning. Science relies heavily on logical reasoning, which includes both inductive and deductive methods. Inductive reasoning allows scientists to develop theories from specific observations, while deductive reasoning helps test these theories through empirical data. We'll also cover common logical fallacies to avoid, ensuring your scientific arguments are robust and credible. Verifiable evidence. At the heart of scientific inquiry is verifiable evidence. This evidence validates hypotheses and supports scientific theories. We'll explore how to critically assess the sources of evidence, emphasizing the importance of peer-reviewed journals and primary data, which are fundamental in upholding the credibility of scientific claims. Prediction and hypothesis. Testing. Prediction is a powerful tool in science used to test the validity of hypotheses. We'll discuss how accurate predictions strengthen theories and look at historical examples to illustrate this point. Understanding the predictive power of hypotheses and their testing is crucial for developing a solid scientific argument. Peer review. The peer review process is critical for maintaining the quality and integrity of scientific research. We'll go through the roles of authors, reviewers, and editors and discuss how to critically evaluate peer-reviewed articles. This process not only ensures the accuracy of scientific knowledge, but also fosters a collaborative scientific community. Implementing principles in instruction. To bring these concepts to life, we'll delve into case studies that highlight both breakthroughs and ethical dilemmas in science. Engage in role-playing activities to simulate ethical decision-making and the peer review process. Classroom discussions, debates on current scientific issues, and reflective writing assignments will further enhance your understanding and application of these principles. Great job with this lesson. Now it's time to check your understanding all about the history and nature of science by logging into your account at teacherpreps.com and completing this practice test. Thanks for watching, and I'll see you in the next lesson. Hello, future educators. In this lesson, you will learn the foundations of physical science. This comprehensive guide will cover the structure and properties of matter to the principles of motion and energy. By the end of this session, you'll be well prepared to tackle these topics on your teacher certification exam. Structure and properties of matter. Understanding the structure and properties of matter is fundamental in physical science. Let's break down some key concepts. Color. Remember, color is not an inherent property, but how substances interact with light. It's crucial for identifying substances and observing changes like temperature or chemical reactions. Mass. A measure of the amount of matter in an object, crucial because it's conserved in both physical and chemical changes. Density. Defined as mass per unit volume, density helps predict whether an object will float or sink in another substance. Hardness. Using the Mohs hardness scale, we can determine the resistance of a material to deformation, which is vital in material selection. Electrical and thermal conductivity. These properties define how well a material can conduct electricity or heat, influencing the use of materials in various applications like wiring and insulation. States of matter and changes in state. Matter exists in three primary states: solids, liquids, and gases, each with unique properties. Solids have a definite shape and volume, with tightly packed particles. Liquids have a definite volume but take the shape of their container. Gases have no fixed shape or volume, filling any container they're in. Changes in state, such as melting, freezing, and vaporization, are physical changes that affect matter's density and volume. Understanding these processes is key to explaining natural phenomena like the water cycle and everyday processes like cooking. Energy and changes in state. Energy plays a crucial role in changes of state. Endothermic processes. These absorb energy, such as melting or evaporation. Exothermic processes. These release energy, like freezing or condensation. Understanding chemical changes. Chemical changes involve the transformation of substances into new ones, a process fundamental to chemistry. Indicators of chemical changes. These include color changes, temperature changes, gas formation, and more. Types of chemical reactions. From synthesis to decomposition and combustion, each type of reaction has distinct characteristics and outcomes. Principles of motion and energy. Motion and energy are cornerstones of physical science. Displacement and velocity. These vector quantities describe motion direction and magnitude. Acceleration. This is the rate of change of velocity, a key concept in understanding forces. Forces. Understanding the push and pull, including gravity and magnetism, is essential for explaining motion. Mixtures and solutions. Mixtures. These can be homogeneous or heterogeneous, each with distinct properties. Solutions. A type of homogeneous mixture where one substance is dissolved in another, crucial in various scientific and industrial applications. Interactions and states of matter. Chemical bonds and intermolecular forces. These interactions determine the physical properties of compounds and their state changes. Phase changes. Learning about the energy involved in these changes helps explain many natural and technological processes. Optical properties of waves. Understanding how light interacts with different mediums is essential in physical science. Let's explore two fundamental phenomena. Reflection. This occurs when light bounces off a surface, such as a mirror, without altering its intrinsic properties but changing its direction. This principle is why you can see your reflection in a mirror. Refraction. This is the bending of light as it passes from one medium to another, changing speed and direction. A common example is the bending of light through a prism, which not only alters its path, but also disperses it into a spectrum of colors. Conservation of energy. Energy conservation is a principle that underpins much of physical science, particularly in discussions about renewable and non-renewable resources. Renewable resources. These include solar, wind, hydropower, biomass, and geothermal energy. They are sustainable and replenish naturally, making them crucial for long-term energy planning. Non-renewable resources. These are resources like fossil fuels and nuclear energy, which are finite and deplete with use. Understanding their impact on the environment and economy is essential for responsible usage. Conservation strategies. Strategies such as promoting energy efficiency, transitioning to renewable energy, and implementing supportive regulations are vital for sustainable development. Forces in motion. In physical science, understanding how different forces affect motion is crucial. Friction. This force opposes the motion of objects in contact. It plays a critical role in everyday activities, such as walking and driving, by preventing slipping and aiding in the stopping of vehicles. Inertia. Defined by Newton's first law of motion, inertia is the tendency of an object to resist changes in its state of motion. The greater the mass of the object, the greater its inertia. Electrical and magnetic forces. These forces govern the attraction or repulsion between charged particles or magnetic poles. They are fundamental to the functioning of many devices, from electric motors to household appliances, forms of energy, and their transformations. Energy can exist in various forms, all of which can transform from one type to another. Kinetic energy, energy due to motion. Anything that moves has kinetic energy, which can be transferred between objects or transformed into other energy forms. Thermal energy. This form of energy is associated with the temperature of an object and is transferred through heat. Chemical energy, stored in the bonds of chemical compounds and released or absorbed during chemical reactions. Potential energy, stored energy due to position, such as water held behind a dam or a stretched spring. Applying knowledge in instruction. As future educators, it's crucial to not only understand these concepts, but also to effectively convey them. Demonstrations and experiments. Use practical demonstrations to show energy transformations, such as converting potential energy into kinetic energy using a pendulum. Problem-solving exercises. Engage students with problems that require the application of the conservation of energy, enhancing their analytical skills. Discussion of real-world applications. Discuss how these principles apply to real-world scenarios, such as in power generation, vehicle design, and environmental conservation. Great! Now check your mastery level by taking the Physical Science Practice Test at teacherpreps.com and get full access to the test prep materials that make passing your teacher certification exam simple. Thank you for watching, and I'll see you in the next lesson. Hello, future teachers. Today, you will learn the key concepts about Earth and space sciences, a crucial component of your teacher certification exam. This session will cover key concepts from astronomy to geology, providing you with the knowledge to not only pass your exam, but also to inspire your future students. Ready? Let's start with astronomy understanding our solar system. Our solar system is a dynamic collection of celestial bodies, each playing a unique role in the cosmic ballet around the sun. Planets. These are major celestial bodies orbiting the sun, each with unique characteristics and atmospheres. Comets. Composed of ice, dust, and rocky material, comets are famous for their spectacular glowing comas and tails that develop when near the sun. Asteroids. These are smaller rocky bodies primarily found in the asteroid belts between Mars and Jupiter, varying greatly in size. Key fact: the Earth, like all planets, orbits the sun in a nearly circular path, contributing to the predictable rising and setting of the sun and other celestial phenomena. Lunar phases and tides. The moon's appearance changes through its monthly cycle due to its position relative to Earth and the sun. Phases of the moon. From the new moon to the full moon, the visible portion of the moon changes, influencing various cultural and natural activities on Earth. Tides. The gravitational pull of the moon and the sun on Earth's oceans causes high and low tides, an essential concept for understanding marine and coastal processes. Now let's talk about Earth's axial tilt and seasons. Earth's tilt on its axis leads to the seasonal variations experienced across the globe, solstices and equinoxes. These are key times of the year that mark the shifts in seasons, with solstices representing the longest and shortest days, and equinoxes marking equal lengths of day and night, time zones, and Earth's rotation. Understanding time zones is crucial for comprehending global time differences. Earth's rotation. A full rotation of the Earth on its axis creates a 24-hour day, divided into 15-degree segments, each representing 1 hour across different time zones. Moving next to geology, which provides insights into Earth's physical structure and the dynamic processes shaping it. Minerals and rocks. Common minerals include quartz and calcite, and rock types such as igneous, sedimentary, and metamorphic. Plate tectonics. This theory explains the movement of Earth's plates and the associated phenomena like earthquakes, volcanoes, and mountain building. Strategies for environmental conservation. Environmental conservation is key to sustaining our planet for future generations. Here are some strategies you should be familiar with. Recycling. This involves collecting and processing materials like paper, glass, plastic, and metal. Recycling helps conserve natural resources, reduce waste, and lower greenhouse gas emissions. Composting. By decomposing organic waste, composting produces nutrient-rich soil, which can enhance plant growth and reduce reliance on chemical fertilizers. Energy conservation. Implementing energy-efficient technologies and practices can significantly reduce energy consumption and environmental impact. Sustainable resource management. This strategy involves the careful and responsible management of natural resources to prevent depletion and ensure long-term sustainability. Meteorology and oceanography. The dynamics of the atmosphere and the ocean play critical roles in weather and climate. Meteorology. The study of the atmosphere and how processes like the water cycle and air movements affect weather patterns. Tools such as thermometers, barometers, and anemometers are crucial for studying meteorological phenomena. Oceanography. This field examines the characteristics of oceans and how ocean currents influence climate across the globe. Understanding phenomena like the global conveyor belt is essential for predicting climate changes. Practical applications and teaching strategies. As future educators, it's important to translate this knowledge into effective teaching strategies. Interactive learning. Engage students with hands-on activities like building simple weather stations or models that demonstrate ocean currents. Real-world problem solving. Encourage students to develop projects that address local environmental issues, applying concepts of recycling, energy conservation, and sustainable practices. Field trips and experiments. Organize visits to recycling centers, conservation parks, or weather stations to provide practical insights into the topics discussed. Check your understanding of these learnings by now logging into your teacherpreps.com account to take the Earth and Space Science practice test. Thanks for watching, and I'll see you in the next video. Welcome to teacherpreps.com. Today, we're diving into the fascinating world of life sciences to help you ace your teacher certification exam. Let's explore the structures, functions, and intricate processes that sustain life on Earth. First up, single-celled organisms, the simplest form of life. These tiny powerhouses like bacteria and protozoa perform all life processes within one cell. They have a cell membrane, cytoplasm, and genetic material. Some even sport flagella or cilia for movement. Contrast that with multicellular organisms, which range from the fungi under your feet to the birds above. These beings have cells organized into complex tissues and organs, each specialized for tasks like absorbing nutrients or oxygenating blood. Now, let's shine some light on photosynthesis. This process is not just about plants turning sunlight into energy. It's the foundation of life, providing oxygen and food to almost every ecosystem. Chloroplasts in plant cells capture sunlight, sparking a series of reactions that transform water and CO2 into glucose and oxygen. Photosynthesis happens in two main stages: the light-dependent reactions and the Calvin cycle. In the thylakoids, sunlight splits water into oxygen, while in the stroma, CO2 is turned into glucose. It's a beautiful, life-sustaining cycle. Switching gears, let's talk about cellular respiration, where cells turn nutrients into energy. Mitochondria play a starring role here. They're like cellular power plants, breaking down glucose to pump out ATP, the energy currency of the cell. Understanding life cycles, from butterflies to frogs to mice, reveals the diverse strategies organisms use to thrive and reproduce. Whether it's metamorphosis or direct development, life finds a way to continue across generations. Now, let's classify life. In taxonomy, we categorize organisms based on shared traits to better understand their evolutionary relationships. From bacteria to plants and animals, each group has a role, especially in food chains, where energy flows from producers like plants to consumers like deer and wolves. Lastly, genetics and heredity. These are the blueprints of life, dictating everything from your eye color to your risk for certain diseases. Understanding genetics helps us grasp how traits are passed down through generations. Genes are the blueprints of life. These segments of DNA reside on chromosomes, long strands wrapped around proteins, and are found in the nucleus of every cell. Each gene holds instructions for making proteins that determine everything from your hair color to your height. Now, let's simplify Mendelian genetics. Gregor Mendel's experiments with pea plants laid the foundation for understanding how traits are passed down through generations. His law of segregation tells us that each organism carries 2 alleles for each trait, which separate during gamete formation, ensuring each gamete carries just 1 allele per trait. To predict how traits might pass from parents to offspring, we use a tool called the Punnett square. It's like a genetic puzzle, showing possible combinations of alleles from the parents and helping us foresee the traits of their children. Moving on to natural selection, nature's own method of ensuring the survival of the fittest. Variations in traits, which are often genetic, can influence an organism's survival. Over time, these advantageous traits become more common, leading to adaptations that are finely tuned to specific environments. Humans have harnessed a similar process known as artificial selection, where we choose specific traits in plants and animals to cultivate. From the juiciest apples to the fastest racehorses, selective breeding allows us to enhance desirable traits over generations. As future educators, how can you bring these complex concepts to life? Engage students with inquiry-based learning, encouraging them to ask questions and conduct experiments. Use age-appropriate resources and integrate technology to make learning interactive and fun. Utilize digital tools and online resources to create a dynamic learning environment. Platforms like Google Classroom and Kahoot not only make learning more interactive, but also help in assessing student understanding through quizzes and interactive games. Assessment is key. From formative assessments like quizzes to summative assessments like end-of-year projects, ensure your methods cater to diverse learning styles. Incorporate performance-based tasks that challenge students to apply their knowledge in practical settings. Want to make sure you're totally ready to pass your teacher certification exam? Log into teacherpreps.com and take the life science practice test now. Thank you for watching, and I'll see you in the next lesson. Welcome to teacherpreps.com. Today, we're diving into the essential world of lab processes, equipment, and safety. If you're preparing for your teacher certification exam, understanding these fundamentals will be key to receiving a pass on your exam. Let's get started with safety, the cornerstone of any lab operation. Adhering to safety regulations isn't just about compliance. It's about creating a culture of responsibility and care. From OSHA standards ensuring safe working conditions to EPA regulations protecting our environment, each guideline plays a crucial role. Preparation is your first step towards safety. Before any experiment, familiarize yourself with the procedures and ensure all safety equipment is at hand. Know where your eye wash stations, safety showers, and fire extinguishers are located, and ensure everyone in the lab knows as well. Personal protective equipment is your best defense against accidents. Safety goggles, gloves, and lab coats aren't just accessories. They are essential tools that protect against chemical splashes, spills, and other hazards. Handling chemicals with care is a fundamental skill. Always check labels and material safety data sheets for hazard information. Use appropriate tools like funnels and pipettes for transferring liquids. And remember the golden rule: always add acid to water, never the other way around, to prevent dangerous reactions. Organization and maintenance are just as important as the experiments themselves. Keep your chemical inventory up to date and ensure all items are clearly labeled and stored properly. Regularly inspect equipment for any signs of wear or damage and conduct routine maintenance to keep everything in working order. In today's digital age, integrating technology into your lab enhances learning and safety. Use digital sensors and probes for precise measurements and employ simulation software to demonstrate experiments that are too risky or complex for a school lab setting. Finally, communication is a key element of scientific inquiry. Whether it's through written reports, presentations, or digital media, encourage your students to share their findings clearly and effectively. This not only reinforces their learning, but enhances their communication skills. Thank you for joining in this lesson. And remember, don't get left behind in your career. Pass your teacher certification exam on your next try. Use the teacherpreps.com test prep materials and make passing simple. Welcome to a crucial chapter of your journey towards acing your elementary teacher certification exam. Today, we'll discuss the Welcome to a crucial chapter of your journey towards acing your elementary teacher certification exam. Today, we'll discuss the world of engineering practices. Now, let's dive deeper into the engineering design processes tailored for your teacher certification exam. We begin with defining problems. Imagine teaching your students to identify real-world issues, such as designing a bridge to help animals safely cross a busy road. Help them clarify the need by discussing who is affected and why the problem needs a solution. Understanding the context is key to meaningful engineering projects. Next, encourage your students to develop and use models. Guide them to create models that represent their solutions, teaching them to predict the outcomes of their designs. Planning and carrying out investigations is crucial. Encourage experimentation and record observations to see how different materials affect their model's performance. Analysis and interpretation of data come next. Show them how to use simple graphs or charts to make sense of the data collected and help them draw conclusions about what their data means in relation to their problem. Incorporating mathematics and computational thinking is essential. Teach them to measure and calculate effectively to predict materials needed and outcomes, helping them recognize patterns in data. Constructing explanations and designing solutions is where creativity meets critical thinking. Guide them to use their data and research to propose solutions, encouraging peer feedback to refine their designs. Engage students in argument from evidence. Facilitate discussions where they present their models and data to support their design decisions, teaching them to critically evaluate their own and others' solutions. Finally, obtaining, evaluating, and communicating information are fundamental skills in any engineer's toolkit. Show them how to gather information from various sources and communicate their findings effectively through presentations and written reports. By mastering these processes, you empower your students not just to solve problems, but to think like engineers. This is the kind of answer you'll want to be looking for when completing your exam. Next, let's explore the fascinating world of materials and their properties. Understanding the relationships and uses of materials like metal, plastic, and wood will help you effectively convey engineering concepts to your students. Metal is known for its high thermal and electrical conductivity, but is often heavy. Plastic, while generally flexible and with low thermal conductivity, offers varying durability. Wood, excellent for structures, provides variable strength and is a poor electrical conductor. To teach these concepts, you'll need to understand key terms. Flexibility, for instance, describes how much a material can bend without breaking. Ductility refers to a material's ability to deform under stress without breaking, like stretching copper wires into thin strands. Thermal conductivity measures how well a material can conduct heat, crucial for materials used near heat sources. Electrical conductivity is the ability of a material to carry an electric current. Melting point, the temperature at which a solid becomes liquid. Moving forward, identifying and communicating design problems is essential for mastering your exam. Look for answers to your multiple-choice questions that require your students to explain their solutions. In every project, make sure you identify answers on your exam that define criteria clearly. Selecting the right tools is next. From measuring tapes to screwdrivers and child-friendly power tools, look for answers to the multiple-choice questions that emphasize safety, accuracy, and quality. Finally, the iterative design process teaches that engineering is never static. Be on the lookout for question selections that support student testing and collaboration with real-world projects in the classroom. With these tools and knowledge, you're well on your way to passing your certification exam and becoming a proficient teacher of elementary engineering. Remember, every lesson you teach builds the problem solvers of tomorrow. As we wrap up, it's time to put your knowledge to the test. Are you ready to see how well prepared you are for the big day? Log into your teacherpreps.com prep account now and take the engineering practices test now.